kernel of V. Okay, kernel of L. And the other one is the range of L. Okay, the range of L is like this. Okay, it's a collection of the vectors in W, such that W equal to LV with some vector V in the vector space V. Okay, so this is called the range of L. Okay, so with the definition of kernel in the range, we can define one more thing called the image. Okay, for any S, which is a subset of V. Okay, LS. Okay, so you map a subset of V. Okay, this represents like some the vectors in W. Okay, such that like W equal to LV for some V in S. This is called like LS is called an image of S. Okay, these definitions are kind of consistent to the function definition. Okay, we talk about the range and the image for function. Okay, we may not talk about like the kernel for function, but we still talk about the range and image, for functions. So these definitions are consistent with the definition of function for the same term. So, and then we have a theorem. Okay, if we have a linear transformation from L to B, okay, then the kernel L is a subspace of B, and the range L is a subspace of W. We can prove that. How many of you still remember how to prove a subspace? What is a subspace? Yeah. By this time, I mean, we actually just did that quiz, right? So I would hope that you still remember. But anyway, I'll treat it as you don't remember anything. Definition of subspace. Okay. So if S is a subset of V, okay, first it's not empty. Okay, and it's satisfied the following two rules, then it is a subspace. For any vector UV in S, U plus V equals S. For any scalar A and the vector U in S, AU is S. Okay? So there are actually three rules. First, this subspace cannot be empty. Second and third are listed here. Okay? So just want you guys to remember. The subspace definition. So now, back to the theorem. So kernel L is a subspace of V. So what is kernel L? is a collection of vectors that will map to 0 in W, right? Okay, previously we already showed that. I mean, we already showed that L0 equal to 0, right? As long as L is a linear transformation, right? As long as L is a linear transformation, then it must map to 0 vector in V into a 0 vector in W, right? So obviously 0 vector in V is in the kernel of L, right? Right? So we have to show that kernel of L is non-empty. So this is the first step. Okay. So then, okay. So if you have U and V, the kernel L, okay, U plus V will be show this. Okay, so from this one, okay, what we know is LU is 0 and LV is 0. Right? And then, okay, let's look at LU plus V. Because L is a linear transformation, so this thing will become LU plus LV. 0 plus 0 equal to 0. Right? Right? Okay. How about the third rule? Third rule is that if scalar, any scalar alpha and the U in kernel L, we show alpha U, okay, is in kernel L, right? So if we have that, that means what? That means LU equal to 0, right? So L alpha U, according to what we have, is equal is the same as alpha LU. Right? You may ask, like, we have to use like U and V. We have to have two vectors in there in order to expand. If you insist, okay, I will write it in that form. So this one is going to be L alpha U plus 0. It's going to be alpha LU plus L 0, right? So this one, we know this is 0. So alpha times 0 plus the second one, we know this one. L0 must be 0. So this one will be 0. So we know that alpha U must be in kernel of L2, right? If you insist that we have to use that two terms in the parentheses. So that's for the kernel of L. Okay, so we have shown kernel of L is a subspace of How about range? collection of vectors in W such that there are some vectors that will map, into this map through this L into like these vectors. Okay, so obviously, okay, first we need to show like the range L is non-empty, it's non-empty. So I mean another very handy thing L0. Okay, because we know like this is the topic, right? This is the U, right? E, right? So we know like 0 must 0 to this one. 0 topic. Okay, the 0 in the vector vector space W must belong to the range L, because we have something that was mapped to this, right? So we know this one is the right? So now it's not empty, and then we need to verify. Okay. So if U, V are in range, we will show that U plus V is in range. Okay, that's one of the rules we need to verify. Okay, what do we mean by U, V in the range? That means L, there exists U prime, V prime in V such that, okay, L U prime equal to U and L V prime equal to, right? According to the definition of range. But we know L is a linear transformation, and L U prime plus V prime equal to L U prime plus L V prime, which will be U plus V. Okay, so in other words, U plus V in W can be mapped by this vector U prime plus V prime plus V prime in V. Okay. So we show that U plus V is in the range of L2. So that's one. Scatter on L. U range. When you show alpha U in range, right? So that's one. Okay. Again, according to the definition, when U is in the range L, there exists a U prime such that L U prime equal to U. Okay? Then L alpha U prime obviously will be alpha minus L U prime, which will be alpha minus U. is in the range of L. Okay. So we have shown that the range of L and the kernel of L both are the subspace. Okay, one belongs to the subspace of W, one is the subspace of W. Okay. So then we can see some material examples of the. Let's take a short break. Okay, when we come back, we will continue our discussion. Okay.
没有到时候也，我要讲，是我们要写。
8到8，正常。所以到时候考完1帮8。那一定我遇过这种情况。
站在车头上，车的时候真的靠一个，然后处理完之后再去放。但是我们这里没有做，我做这个是应该是之后换的，就是开发的那个，它部署的话那个真的是叫不好上，专长。没有这么重要，去公司里面你遇到的错误，你解决它。
我写很多，我写很长。
没办法，这就是工作。不然这边你到时候一模一样错误啊，就要再找一遍，你会更提效。
那公司有讲，奇怪。
是啊。 非常不是看不到，
我谁都有人去。
想看后面有没有写。收影片的那种放，
今天要去太阳了。